Hello everyone, welcome to another video tutorial. Let's continue solving the problems of the chapter 2. Today I try to complete the problems of this chapter. Problem 32. A single phase 200 kVA 2100 to 210 volts 60 Hz transformer has the following characteristics. The impedance of the high voltage winding is 0.25 plus J 1.5 with the low voltage winding short circuited. Yes, so this is the impedance of the short circuit test. That is actually the Z equivalent. This is the equivalent resistance and this is the equivalent leakage reactance. The admittance inversal impedance of the low voltage winding is this one with the high voltage winding open circuited. Yes, this is the value of the admittance in the open circuit test, right? So the inverse of this, we can calculate the impedance and then we can calculate the equivalent core resistance and the magnetizing reactance. A. Taking the transformer rating as base, determine the base values of the power, voltage, current, and impedance for both the high voltage and low voltage sides of the transformer. So, what are base values? If we take the apparent power and voltage, the rated values, for the base, we can calculate other quantities. So you can check this section for the chapter 2 per unit system. In the per unit system, right, to establish a per unit system, we have these four variables. We should take two of them and then we can calculate the rest. You know that. So if we take this value for the base apparent power and rated voltage, for the base voltage, we can calculate the base currents and the base impedances. So what is the value of the base current for the high voltage is the apparent power divided by the voltage is equal to 95.2, and the base current for the secondary side, the low voltage side, is 952. So yes, how we can calculate the base value for the impedance? We have these two equations. We can use either this equation, V base, I base, or this equation, V base to the power 2 divided by P base. So I calculated the base impedance for the high voltage side. Here, V high voltage, I high voltage, 22.05. And what is the value of the Z base for the low voltage side? Again, we have this fraction. So let's check the numbers. We have the solution of the part A here. The base value of the apparent power, voltage, the current, and this is the base impedance. Also, we have these base values for the low voltage side. Only the solution of the part A is given here. Okay, so part B, determine the per unit value of the equivalent resistance and leakage reactance of the transformer. The Z equivalent is given here, 0.25 plus J 1.5 5. So this is measured when the low voltage side is short circuited. This is the equivalent, right, impedance for the high voltage side. And to calculate the Z equivalent in per unit, we need to divide the Z equivalent for the high voltage by the corresponding base impedance. Base impedance of the high voltage side, not low voltage. So here we have the per unit equivalent impedance. This is the per unit equivalent resistance, and this is the per unit equivalent leakage reactance. Part C, determine the per unit value of the excitation current at rated voltage. What is the excitation current? Is the current of the excitation branch. Yes, when one side is open circuit. So the admittance in the open circuit test is given. The admittance of the open circuit for the low voltage side. What is the value of the no load current? Is the voltage of the low voltage side times the absolute value of the admittance. You know this from the circuit theory course. Yes, the value of the no load current is 16.6. We can calculate the per unit value. This is for the low voltage side. What is the value of the base current for the low voltage side? Is this one, 952. So this is the per unit value of the excitation current, the no load current, below 2%. Okay, so also you know the concepts for this. Okay, so part D, determine the per unit value of the total power loss in the transformer at full load output condition. So to calculate the per unit value of total losses, we need to calculate the per unit value of the core loss and per unit value of the copper loss for the full load. So here we have this admittance. How much is the core loss? Is the, you know, if we consider this branch, this excitation branch, this is the resistance and this is the magnetizing reactance. So this is actually V to the power 2, V low voltage, times the real part of the admittance. That is conductance, right? So the real part of the admittance is conductance, and here we have the real part. So V to the power 2 times the real part is the iron loss. Iron loss divided by the apparent power is the per unit value of the iron loss, the core loss. So yes, I think it's better if I show the admittance using the correct letter. This is why you know that the admittance is the inverse of the impedance. Admittance is 1 divided by Z, that is equal to conductance plus J times B. Okay, susceptance. So here we know that the loss for this resistance is V2 times the conductance, the real part of the admittance. So here I used this equation to calculate the core loss. this one with low voltage to the power 2 times the conductance. So this is the per unit value of the iron loss. What about the copper loss? The value of the copper loss at full load is equal to the right per unit value of the equivalent resistance. We can calculate the full load copper loss, multiply this number by the current and divide it by the apparent power. But we know this concept from here. Chapter 2. Here we have this subsection, full load copper loss. The full load copper loss is R equivalent, for example, for the side 1, times the rated current for the side 1 to the power 2. This. So how much is the per unit value? We need to divide it by the apparent power, the P base. So P base is V rated, I rated. This is V rated divided by I rated, right? You can simplify this fraction, and finally we will have this. The transformer resistance expressed in per unit form also represents the full load copper loss in per unit form. So the per unit full load copper loss is equal to the per unit equivalent resistance. This number, yes, this is the per unit equivalent resistance that is equal to the per unit value of the full load copper loss, this number. And the total per unit value for all losses is summation of these two, that is 0.016 per unit. Okay, so you can redo the calculations and write and solve this problem yourself again. Problem 33. A single phase transformer has an equivalent leakage reactance of 0.04 per unit. This is the value of the leakage reactance, the equivalent. The full load copper loss is 0.015 per unit. And the no load power loss at rated voltage is 1%, right? 0.01 per unit. The transformer supplies full load power at the rated voltage and 0.85 lagging power factor. A. Determine the efficiency of the transformer. Determine the voltage regulation. So here is the model of the transformer that I am going to use it for calculation of the voltage regulation. And here is the equation that I am going to calculate the efficiency. So yes, we calculated the efficiency multiple times in the previous problems. We used the real values. This time we are going to use per unit numbers. So here the transformer delivers the rated power 1 per unit. Okay, what is the value of the power factor? 0.85. So we should multiply this by 0.85 to calculate the real output power of the transformer. Okay, this is the real output power of the transformer in per unit. What is the value of the iron loss in per unit is given here, 0.01. And the full load copper loss in per unit is given here. Okay, so the value of the efficiency will be equal to 97.1%. Yes. And how we can calculate the voltage regulation? This is the equivalent circuit. And here is the equation that I'm going to use for calculation of the voltage regulation. Yes, let's consider the V2 in its per unit format, the rated value, and calculate the V1 for the full load condition. So V1 in per unit for the full load operating condition is V2 per unit rated Z equivalent times I per unit. What is the value of the Z equivalent? Is the R equivalent in per unit plus the leakage reactance in per unit. The value of the leakage reactance in per unit is given here, and again we know this, the per unit value of the resistance is equal to the per unit value of the full load copper losses. This number is given here, 0.015. So what is the value of the current? I per unit is the rated one. The transformer delivers the full load. So if you replace the numbers, the value of the voltage regulation will be 3.4%. So as you can see here, using per unit values, we have much, right, more efficient computations. So computations are more efficient in compared with the previous methods that we used real values. So this is good. Problem 34. A single phase 10 kVA 7500 to 250 volts 60 hertz transformer has Z equivalent, this one, or equivalent equal to 60 per unit, and the magnetizing reactance 20 per unit. A. Determine the equivalent circuit in ohmic values referred to the low voltage side. Okay, so in this case, in this problem, the per unit values for the model, the equivalent model, are given, and we should calculate real ohmic values. So first of all, we should calculate the base current and the base impedance for the low voltage side. Then we can calculate the ohmic values, considering this equivalent impedance and the core resistance and the magnetizing reactance. The base value of the current for the low voltage side is here, the apparent power divided by the voltage. The low voltage side is 250. 10 kVA is 40 amps. What is the value of the Z base? The base impedance for the low voltage side is voltage divided by current. 250 divided by 40 is 6.25 ohm. So the Z equivalent for the low voltage side is Z equivalent per unit times the Z base for the low voltage side. Here we have the Z equivalent in per unit times 6.25 is this one. So this is the Z equivalent in ohmic values. Here the unit is ohm. Okay, per unit values are unitless, you know that. What is the value of the magnetizing reactance for the low voltage side? Is 20 times the Z base, 6.25, 125. And what is the value of the equivalent core resistance for the low voltage side? Is the RC in per unit, 60 times the Z base for the low voltage. that is this one, 375 ohm. So here we calculated the ohmic values, and this is the equivalent circuit model of the transformer referred to the low voltage side. Here we have the equivalent core resistance, the magnetizing reactance, the R equivalent, and the equivalent leakage reactance. So, part B, the high voltage winding is connected to a 7500 volts supply and a load of 5 with this angle 90 degrees is connected to the low voltage side. Determine the load voltage and the load current. Determine the voltage regulation. So here we have this circuit, just we need to consider this load impedance here. The amplitude of the impedance is given 5, but we don't know that this load is inductive or capacitive, right? Is not mentioned in the part B. So I solved this problem for both cases, considering inductive load or a capacitive load. So here, when we connect this voltage source to the primary, the value of V1 prime, the value of the voltage referred to the secondary is 250. What is the value of the I load in this case? Is 250 divided by these two impedances, the summation, okay? The summation of the Z equivalent for the low voltage side plus the load impedance. You should write a KVL here. So, yes, 250. Let's consider the angle of this phasor as the base divided by this summation. For the inductive load, we have this plus 5J. This one, the value of the load current is 46.5. This is the angle. So we can calculate the load voltage, that is the load impedance times the load current. Here is the calculation, and this is the value of the load voltage, 232.5. So we can calculate the voltage regulation using this equation. V2 for the no load minus V2 for the full load. We don't have primes, yes, because we are doing calculations for the secondary side. V2 for the no load when the load current is 0 is equal to V1 prime. So in this case, the value of the voltage regulation is 7.53%. We can repeat these calculations considering a capacitive load. For the capacitive load, the value of the load impedance is negative 5J. So if you repeat the calculations, the value of the load current will be equal to 54. The value of the load voltage is 270, and this is the value of the voltage regulation. Let's check the numbers. Here we have the solution of this problem. Okay, the value of the equivalent core resistance 375, yes. The value of the magnetizing reactance 125. The value of the equivalent resistance for the low voltage side are the same, and X equivalent. The value of the load voltage 200 and 70. Yes, this one. So the load is capacitive, but we did calculations for both cases. The numbers that are here are for capacitive load. This is the value of the load current, 54.04, and the value of the voltage regulation is negative 7.5%, this number. Anyway, so you can repeat, right, solving this problem. Let's go for the last problem of the chapter 2, problem 35. A single phase 10 kVA 2200 to 220 volts 60 Hz transformer has the following characteristics. No load core loss is 100 and full load copper loss is 215. Write a computer program to study the variation of efficiency with output kVA load and the power factor. The program should A. Yield the results in a tabular form showing the power factor per unit kVA, load fraction, and efficiency. Produce a plot of efficiency versus percent kVA load, this one, for power factors in this range 1, 0.8, 0.4, 6, and zero point 0.2. Also, we should generate this table, not too complex. We did it before for one problem, and we can repeat the code. So here, let's check the code for problem 35. The value of the core loss is given here, 100, and the value of the full load copper loss is 215. We have this value here, and the value of the rated apparent power is 10 kVA. So yes, we have this for loop. I change the value of the power factor, and inside this loop we change the value of the load fraction from 0.4 to 1. For example, consider 10 points for the load fraction, and then calculate the efficiency using this equation, right, that we used for calculation of the efficiency as a function of the load fraction. We used it for one of, I think, this problem. Okay, so considering the load fraction, we can calculate the efficiency. I implemented the equation here. This is the output power for this power factor and this load fraction, the core loss and the copper loss for any load fraction is the load fraction to the power 2 times the full load copper loss. Then I display this string in the command window, and then I display this matrix to actually generate this table. Right, simply we can generate this table. Here I only considered 10 numbers for the load fraction from 0.4 to 1. And finally we can plot the efficiency versus load fraction for different power factors from 0.4 to 1. Okay, so if I run the code, here in the command window, you can see tables. We change the power factor, the load fraction, and we have efficiency here for different cases. right? We change the value of the power factor from zero point 0.4, zero point 0.6, zero point 0.8, and 1. Here is the efficiency graph. The efficiency versus the load fraction for different power factors. As you know, when the load power factor increases, efficiency increases. Maximum efficiency occurs for a specific value of the load fraction. You know that number. Yes, that is the square root of the core loss divided by the full load copper loss. Anyway, so you can rewrite this M file to solve this problem 35. Okay, we completed all problems of the chapter 2. I hope you found these videos useful for your exam, and let's continue solving the problems of the chapter 3 in the next video.